objectives. And to start off going over routing, I have this whiteboard that I'm going to pull up, and this is where we're going to start. Let me get the faces out of the way. And to start off going over routing, one sec. Okay, cool. So let me start recording this.
Recording in progress.
So today we're going to get through old domain 2, and since we missed last Friday, I'm going to make up for that Thursday. I'll send out an email to you guys, so it'll be Wednesday, Thursday, Friday this week. The vouchers I'm going to order Wednesday, and then they'll be in your account, and I'll send an email to you guys on Friday. So they'll be in your account on the academy.trebetech.com on Friday, and I'll also send you an email with your voucher and your certificate of completion. So if you're using this course to get your continuing education units, that'll work too. It'll be like a 50-hour certificate. All right, so let's go ahead and jump right into it. So today, again, we're going over routing. So routing fundamentals. All righty. So when we're thinking about what routing is, the whole purpose of a router or the layer 3 device is to take traffic from a source and send it off to a destination. So a router's whole purpose is to send traffic based on destination IP address. So when I go on my computer and I type in google.com, now obviously there's some DNS in the background, don't worry about that, but I make an IP-based packet, and that packet's going to have a layer 3 header, and that layer 3 header is going to have a source and destination IP. Now again, I'm on my workstation here. This is the visual I'm trying to paint. So when I send that packet off, I send it out my Ethernet port, out my wireless LAN connection. That destination IP or that packet's eventually going to hit my router. Now whether that's a router, a multi-layer switch, or a firewall, it doesn't matter, a routing device, it's going to look at that packet and it's going to inspect that destination IP address. It's going to look at that destination IP address and it's going to reference something called the global routing table. And if there is a match for that destination IP or a subnet in which that destination IP falls under, in that global routing table, it's going to tell it how to send that traffic or where the next hop is for that traffic. So to, take a step back again, a router's whole purpose is to send traffic based on destination IP address. And the router has what's called a global routing table that's going to decide where to send that traffic. And if the destination IP address is on a remote subnet, the routing table will have a mapping of where to send that traffic. Essentially just saying, like if you think of the routing table as like an Excel spreadsheet, it's going to say, hey, this subnet, if we get a packet that's destined for this subnet, a remote prefix, synonymous, send it out gig 00, or send it out, fast Ethernet, whatever the case may be. So that's that mapping. If destination IP has a match on the routing table, it falls under this subnet that's in our routing table, send it out this way, okay? Now, how do we build that routing table? So we build that routing table with routing protocols, which we're going to get into. So that's static routing, that's dynamic routing protocols, interior gateway, and exterior gateway protocols. We'll break that all down on our slideshow. Now, what happens if that router does not have a route? Meaning we have a packet from our users, an inbound packet from our users. We see they're trying to reach, let's say, the 1.1.3.2 IP address. That's in their destination IP and their layer 3 header. So I reference my routing table and say, hey, do I know where to send 1.1.3.2? I don't. I don't have a route that matches or a subnet that matches that destination IP address. So what I'm going to do, I'm going to discard that packet. That is as Barney style, as broken down as we can explain routing fundamentals. Now, let's take a look at our little diagram here. So let's take a look at router 2. So when we talk about routing, we know that the whole purpose is just to take a source and get it to a destination. So, for example, Bob right here. Bob's IP address is 192.168.1.2, and he wants to talk to 192.168.3.24. So this is like his layer 3 header. Okay, my width is good. So this is like his layer 3 header. So when that comes up to the router, because remember, when we want to talk outside our subnet, so he wants to talk outside his subnet, we have to go to our default gateway. And that default gateway is a router, and that's going to determine where to send the packet. So this comes up to the router. R2 is then, and let me actually delete this, hold on. Okay. R2 is going to receive that inbound and say, okay, cool. So from my gig 03 port, I have a packet that I need to route for. Let me inspect its destination IP. It needs to head to 192.168.3.24. So let me reference my routing table. Now this is obviously like a pseudo routing table, meaning this is not how it actually is going to look, but this is a way to, this is how it works. It really is just like a spreadsheet of, do I know where something is and what's my next hop? So if we look at the routing table here, is there a match for the 192.168.3.24 IP address? No, there is not. Currently, R2, in our made-up scenario, doesn't know where to send it, so it's going to discard it. So that's a problem. Obviously, as network engineers and network administrators, our whole job is to ensure that packets reach their destination, that you can browse the web, that you can reach a destination with the port and application that you need to, right? Like HTTP, whatever the case may be, a video conferencing, whatever, right? So now that goes into, okay, well, how do we build this routing table? Remember I told you we build our routing tables using routing protocols. There's a couple major categories. So there's interior gateway protocols and there's exterior gateway protocols. So IGPs, and I'll just type this right here, stand for interior gateway protocols. Interior gateway protocols are going to do routing within a domain, okay? So when we think about enterprise networking, when I say enterprise, remember, that's like your office. So if you guys work at, example.com, you go to a 12-story office floor with 1,000 users there, that's your local enterprise, okay? And you may have spoke offices in Houston, Texas. Maybe you're in New York. You have spoke offices in Chicago. That's your enterprise. That's all your network. That's all the users you communicate with on your local enterprise. So when the routers from your spoke offices to your headquarters are routing traffic to each other, they're going to use an interior gateway protocol. And those interior gateway protocols are going to share with their routing neighbors like R3, R4, R1, are all going to share with R2 what they know about. They do this with a routing protocol. So within interior gateway protocols, we have routing protocols like RIP, OSPF, EIGRP, and like ISIS. Now, out of all those routing protocols, these IGPs, we're also going to have other ways to define them. So RIP is going to be what's called a distance vector. We'll break this down a little bit. OSPF and ISIS, I should have put those like together, are going to be what's called a link state. A link state routing protocol. And then EIGRP is called like an advanced distance vector protocol. In the actual slides, guys, we'll go over this, okay? So whatever we configure here, so if we configure OSPF on R3, R4, R2, and R1, that's going to be the routing protocol that shares routes with its neighbors. So what we mean by that is R4 will tell R2 about the 192.168.3.0 network. Okay? It'll tell its neighbor about the networks it knows about via a routing protocol. Now, OSPF is what I'm using in my example. That could be EIGRP. That could be RIP. That could be ISIS. And when it sends that to R2, R2's going to, as long as they come up as routing neighbors, and there's a process there that we're going to learn about, they come up as routing neighbors, they're sharing routes via OSPF, as long as everything matches, it's going to take that route that it learned and say, okay, I know where this 192.168.3.0/24 is. It is off my gig 02 interface. That's where I learned about it from. So now when R2 receives that destination IP from Bob, it's going to say, oh, I know where to send you. You're destined for 192.168.3.24. That's in my routing table. Your next hop is out gig 02. That's going to send it to R4. And then R4 is going to receive that, and it's going to reference its routing table. It's going to say, oh, I see I'm getting a packet off gig 02 here that needs to talk to 192.168.3.24. Then R4 is going to reference its routing table, and it's going to say, oh, yeah, I know where 192.168.3.24 is. It's hanging off my LAN here. So I'm going to send it out my LAN, and then it's going to go to Alice, right? This is Alice's IP address, guys, in this scenario. And that's the entire flow. That's as dumbed down as I can make it, okay? That is routing. Now, you may be asking yourselves, well, it can't be that simple. And for the most part, you're right. It's not that simple. Sometimes we get into scenarios where maybe R3 is also advertising .3, and maybe we're doing ERGRP right here. And then between R4 and R2, we're advertising via RIP the same exact subnet. So which one is R2 going to place in the routing table? And we'll get into that after we get over the slides, okay? So those are the routing fundamentals. That's how a router is routing IP-based traffic. It's building a routing table based off what it learns about from its neighbors. And then, of course, we have its local connected things here. It's going to know what it's connected to it. So R2 has 4 Ethernet connections. So it's going to know about this network, this network, this network, or excuse me, R2, and this network automatically, right? That's what it's automatically going to know about. But then it's going to learn from its neighbors all these other remote subnets, or prefixes. They're also called prefixes. Now, it gets tricky, right? What I just showed you is when R2 learns about the 192.168.3 network from R3 and R4 with different routing protocols, and maybe like a different, interface. Maybe this is like a T1, right? Which is 1.544 megabit speeds. What's it going to put in the routing table now? We're going to dive into that once we get through some slides, okay? But building the routing table is kind of the next step into understanding routing. And that will be down here. Selecting the best route is what we call it. But before we get into that, let's go ahead and go through some slides now, because now we have to just get through some basics like, hey, what is static routing, things like that, okay? So let's get through some of these basics. Okay, so static routing. That's also like an interior gateway protocol. It's done, I say it's done within the enterprise, but static routing can be done anywhere, whether that's a connection off to another autonomous system, like another internet service provider, or it could just be your little small office, home office networks. We have default routes out. So like at your house right now, if you're watching this Zoom call, you probably just have your router modem from your ISP. Your ISP being Spectrum, whatever fiber provider you have. Time Warner Cable is what it used to be called, whatever you may have there. And that router is just sending a default route out. That's a static route, pretty much saying our only way to the internet is to our ISP. That's the only way we're going to send traffic, okay? So static routing. Static routing is a simple form of routing where a network administrator manually configures the routing table on each router. So in static routing, the route to a specified network or device is explicitly defined. So what I mean by that is, with like OSPF, BGP, EIGRP, RIP, that's all routing protocols that I configure the routing protocol, but then the router will use that technology, that routing protocol, to send hello messages and to send updates. Whereas static routing, you have to explicitly say, I want to go over there. I want to hit that remote subnet. So it's a lot more manual configuration, okay? That's static routing. We have different types of static routes. So we have floating static routes. So a floating static route is a backup static route. So imagine we have a primary link here, like a fiber uplink, and this connection we're using OSPF. And then we have a T1 link here that's 1.54 megabits, and gigabit speed's 1,000 megabits, so we know which one we want to use. So I can configure a floating static route here. That's the backup. That pretty much says, hey, If this OSPF route goes down, I'll use my backup here. That's how we configure it. I'm not going over syntax right now, guys, because this is Cisco iOS, and the CompTIA Network Plus exam is multi-vendor, right? So it's not important you memorize that syntax. Then we have a host route. So this is like a static route that just goes to a single host. So this is where we have, hey, we have two routes here. We have two links, a primary, secondary link. We want all traffic going over our primary link, but let's say there's a specific server. Let's say .3 here. I want to talk to .3 only on my secondary link. Well, we can set up a host route that says, hey, on R1, when I want to talk to .3, I'm going to go out gig 00, but only .3, not the entire subnet, just .3. That's a host route. Okay, now before we move on, let's take a look. Let's go over a quick little lab here. Alrighty. Okay, so we have our environment here. So let's take a look at this. Let me bring up my pen real quick. Okay, so we're going to do, this is the only demonstration we'll probably do today too, just to let you guys know. Okay, so we have R1 here and R2 here that we're going to configure. So we have users over here hanging off R1. We have this VLAN 10 and this VLAN 20, but it's just a subnet, as you guys can see. It's just a subnet, right? And then we have users over here hanging off R2. And the goal is we want users to be able to talk to each other. We want the users from both sides to be able to talk to each other. So what do we have to configure? We have to configure routing. So between R1 and R2, we're going to have this point-to-point link. And then what we're going to configure here is a static route over to these networks over here on both routers, okay? So both routers will need the static route. I'm going to show you this manual configuration, right, of why it's, static routes are not recommended for anything really more complex than this. Now, obviously, I've used them in some scenarios in a bigger complex network, but just for the Network Plus, right, this will give us our basics. So again, I'm going to be on a Cisco iOS doing this. Do not expect on the actual exam Cisco iOS to be like the default syntax you'll use, but typically, well, I haven't seen the exam, but maybe if I just had a hunch that it will be showing kind of how to do configuration like this in some questions, okay? So let me zoom in here. Okay, so let's get our bearings here. So I'm going to do show IP interface brief. So we're configured over here on R2. Looks like R1 we don't have any configuration. So we're going to do some quick configuration here. I'm just going to give it a host name. We'll say R1. And then we got to set up IP addressing. So gig 00. We're going to set IP address 75000. 254, we're going to no shut. And then we're going to make some sub interfaces here. This is kind of like old school traditional networking way to set up network segmentation, do some sub interfaces and VLANs. Now again, if you're just you're like, dude, you're just jumping right into this. Again, I'm just setting up IP addressing that we're going to go over in, I think, domain 5. Right now, I'm just setting this up so we can get to the point of setting up a static route, okay? So I'm just giving IP addressing so that our users can get an IP address and we can test out our routing, okay? All right. So now if we type in show IP interface brief, and again, this is syntax on the Cisco iOS, we can see that our interfaces are configured, and we put in that no shut command because this is administratively shut down here, right? Now this is Cisco iOS. Now if you're used to other devices, like let's say, I don't know, Fortinet, Juniper, really anything, it may not, it may look a little different, right? Especially if you're used to like a GUI, you may not be working in a CLI. But all right, so now here's the deal. R1 over here needs to be able to reach these networks. So if we configure a static route, what I'm going to do from R1 is I'm going to say, hey, I need to reach this subnet, 16.1.0, 10.0. It's a whole subnet, the subnet mask, and to reach that, I got to go out gig 00. Because remember, that's the point-to-point connection that connects me to R2. So my next hop will be out gig 00. I can do up arrow here to bring back that line. It'll be dot 20. That's to reach the remote subnet that I do not know about. And then in R2, we got to do the same thing. It'll be IP route, and we need to reach these networks here, the 192 networks hanging off R1. So it'll be 192.168.10.0, the subnet mask, out gig 00, that point-to-point, the thing that connects us to R1. So this is the manual configuration, okay? The manual configuration of static routes. And now if we want to look at our routing table in Cisco, it's called show IP route. We can see those static routes here. Now how do I know those are our static routes? We have these codes that have the S next to it, saying it's a static route, okay? Let's check that on R2. So there's static routes. And then in here we also have a default route that was previously configured. I'll show you how we do that. That little asterisk there, that default route, pretty much is a catch-all saying, hey, if my users try to reach an IP address that doesn't fall under any of these more specific subnets here, send them out gig 00. This is the catch-all. So catch any other IP addresses that are not part of this right here that I'm highlighting, okay? So let's do our ping test. From R2, I'm going to ping our point-to-point neighbor. So ping 75000, we can reach it. And then I want to ping the remote networks. And there we go. We can ping the subnets hanging off R1. That's static route, that's manual configuration. So it may seem pretty simple, pretty easy, right? Well, imagine we get more complex though. We add a bunch of different neighboring routers with their own LANs. It can get confusing. That's where dynamic routing comes in. That's where we start implementing our interior gateway protocols. Now imagine we have our own enterprise. We have our own routing domain. So we're a part of the example.com. We have tens of thousands of users with offices everywhere. And we have our own autonomous system. And now we need to share our networks with an ISP. Then we get into what's called exterior gateway protocols. That's like BGP. So let's go to our slides here. So that was manual configuration, static routing. Okay, to kind of slow it down a little bit, remember, everything we're doing here is just to accomplish the main goal of our router, which is source to destination. Look at destination IP addresses, reference your routing table, and send it where it needs to go so that our users can reach their destination. That is the ultimate goal of a router, inspecting those layer 3 headers. Now, I've been teaching for 25 minutes here. Let's go ahead and take a 10-minute break. We'll come back. We're going to go through all these slides, and then I'm just going to go over the basics here of these routing protocols that you guys need to know about for the Network Plus exam, no configuration. We'll get here, and we're going to stop right here. We're going to go back to the whiteboard, and then hopefully we finish up routing before like 7 p.m. So let's put 10 minutes on the clock. We'll come back in 10. Okay, let's jump right back into it, guys. So we just went over the purpose of routing, how a router builds a routing table based off information from its routing neighbors and then what it has locally, and that its main purpose is to route traffic from source to destination. And then I showed you the very basic static routing, how to manually configure a router to reach out to remote subnets that it does not know about locally. Well, now we're going to get into dynamic routing. So the first dynamic routing protocol we're going to get into is called BGP. This is called an exterior gateway protocol. So this is a routing protocol that autonomous systems use to route traffic between each other. So to break that down as simple as I can, imagine your ISP, Verizon, AT&T, Spectrum, Metronet, Google Fiber, or whatever the case may be. They have to route the internet. So every single user that hangs off that ISP, that needs to talk to a web server hanging off another ISP or in the cloud somewhere, all that traffic has to get routed globally. And the routing protocol that achieves this is called BGP, the Border Gateway Protocol. This is a protocol that routes traffic between autonomous systems. Yes, at the end of the day, there is a router there with a connection to another router that sits in another autonomous system. And yes, at the end of the day, it's just sharing with its routing neighbor what it knows about, which the internet routing table, that's a lot of /8s, a lot of big subnets that it's going to be routing for, okay? But that's what it is. And it's a path vector protocol. So different than our link state and distance vector protocols, it's kind of its own category sitting off the side. It's not an IGP, interior gateway protocol. It's an EGP, an exterior gateway protocol. And again, that routes between autonomous systems. So BGP uses attributes like AS, path, and next hop, and policy to determine the best path. So what are we talking about there? Pretty much the path selection. So how does BGP determine the best path to get to a destination? Because imagine we have a user sitting off here. Now remember, this is like big time, right? This is an ISP with a user down here in Houston, Texas, and this ISP is doing all the routing for that whole region of Texas, whatever the case may be, and needs to talk to a server hanging off this ISP. So obviously you would think, oh, the best path here is to come this way and over here. But don't we have an alternative path? We have this alternative path here. So BGP routers that are routing for these ISPs, how does it determine the best path? Well, there's attributes like the autonomous system path, the next hop, and other policies. There's actually like, I think, 11 different ways that BGP can determine the best path. But in short, to keep it simple, because the Network Plus exam, it's going to say, well, I'm learning about this subnet from this autonomous system. So attached on that, right, will be like, hey, you're learning about that network via AS2335. And then when it comes this way, it's going to be like, hey, to learn about this 7 network, you're going to learn about it from AS4778 and AS2335. So in this scenario, what's the shortest path here, right? The best path selection is going to be just going over here because that's less hops, okay? So that's as basic as BGP as we're going to get. It can and it will be way more complicated if you ever get to an enterprise or an ISP that says, hey, we do BGP routing. So just, we'll keep it that simple. All right, next slide about BGP. So how does BGP come up? How does BGP peer with its neighbors? And let's just learn some facts about it that you may see on the exam. So eBGP neighbors or peers are manually configured to establish a TCP connection using port 179. So we say manually configured. Like if I was configuring BGP here, I would go on R1 and I would type in neighbor, an IP address, and then I would say its AS system is 500. So it'd be neighbor, the IP address of that neighbor, and then remote autonomous system 500. That's how I would do that manual configuration of BGP peers. And then R2 would do the same thing. R2 would do the exact same thing back to R1. It'd be neighbor, R1's IP address, remote AS, like AS600. And once we configure that, and we have other options here. Typically neighbors are directly connected, but they don't have to be. Like between R1 and R2 here could be a whole bunch of different routers in this little cloud ISP we have here because it's TCP. So anyways, so once we execute those commands, we're going to establish our TCP connection, and then we're going to go to an open set state. We're waiting for, our neighbors to communicate. Then we're going to go to an open confirm state saying, hey, we've learned from our neighbors. We're going to become established, and then we're going to get our routing updates where our neighbors are going to share the BGP tables with each other. So we go through all this to get to this stage where we're actually sharing with our neighbors the remote subnets that we know about, okay? So that is BGP, and that's as simple as I think I want to make BGP for you guys in this Network Plus exam. Okay, the next routing protocol we're going to talk about is EIGRP. So EIGRP stands for the Enhanced Interior Gateway Protocol, and it's known as an Advanced Distance Vector Protocol. It uses the dual algorithm as a way to select the best routes for EIGRP, and it's a dynamic routing protocol that creates a loop-free path. Yes, I'm going through this rather quick, okay? So EIGRP-enabled routers, so when we have two routers talking EIGRP, they're going to send a hello packet, and in that hello packet, we're going to have values that need to match. The autonomous system number, the K values in that hello packet, and authentication if configured. So once neighborship is established, we're going to be sending hellos every 10 seconds, and if we don't receive a hello for 40 seconds, we're going to consider our neighbor down. But then once that neighborship is fully established, we're then going to start sending updates. Now, as neighbors, we're going to start sending EIGRP update packets. And through those update packets, we're going to build what's called the topology table. Once we build that topology table, we're going to execute that dual algorithm, and we're going to place the best routes into the routing table. OSPF, another dynamic routing protocol that the CompTIA Network Plus wants you to know about. This is a link state routing protocol, and it's going to have a similar function to establishing OSPF routing neighbors. So OSPF-enabled interfaces, because it's a link state routing protocol, so that's gig 0 here in this scenario. Once we configure OSPF on the router, they're also going to start sending hello packets to each other. And OSPF, the hello packets also need matching parameters for R1 and R2 in our slide here to become OSPF neighbors. That's going to be the hello and hold timers. That's going to be the area ID, and the MTU needs to match. So area ID, hello and hold timers, and the MTU needs to match for OSPF-enabled routers to become neighbors. And in these interior gateway protocols, RIP, EIGRP, OSPF, they do have to be directly connected, unlike BGP, to become routing neighbors. Once our neighborship comes up, OSPF is going to start sharing with its neighbors what's called its link state database. We do this through LSAs, link state advertisements. So we're going to be sending LSA updates and acknowledgments between our neighbors to build what's called a link state database. Once that link state database is converged with every single OSPF routing neighbor, we're then going to execute the shortest path first algorithm. That's the SPF in OSPF. Once we execute that shortest path first algorithm, we're going to place the best routes into our routing table. And once we do that, we call that full convergence. Now, the actual metric for OSPF is what's called a reference bandwidth. It uses bandwidth as its metric to place the best routes. We also call this its cost, okay? The cost. That's something you may need to know. Bandwidth is the OSPF cost, and that's the metric we use to place the best routes into the routing table using OSPF. All right, now we're going to jump into route selection. So I just taught you about different routing protocols, and you're probably smoke coming out of your ears. But remember our fundamentals. Routers are there to take an IP packet, look at the destination IP, and send it off to its destination. It does that by referencing its global routing table. We build our global routing table by information from our routing neighbors using a routing protocol. Now, how we get there, EIGRP, OSPF, and all the intricacies in there, in those protocols, we're not going to go over in this Network Plus, but what we do need to know is how a router selects the best route. it's going to go based off 3 rules, and it's in order. The longest prefix length is always going to be preferred. So that's the longest prefix length is always going to be preferred. And then it's going to go into something called administrative distance. And then it's going to go into something called its metric. That's the 3 rules on how we place the best routes into our global routing table. Let's go back to our whiteboard here. Okay. So let's go over selecting the best route. So every device has a routing table that's going to determine the best path for IP-based traffic. Meaning, if I am a router that I'm learning about remote subnets, and I learn about remote subnets 2 different ways, I have to figure out which way is the best. So every device has a routing table that determines the best path for IP-based traffic. Now, a router has its own rules for selecting the best path. That starts with the longest prefix. The longest prefix will always be preferred for duplicate paths to the same destination. So what we mean by that is if I'm learning about, if I'm a router, right? I'm a router here. Okay, I'm a router here. And I'm connected to my routing neighbors over here. And here I learned 10.0.0.0. Actually, hold on. This looks, I don't know. This looks kind of bad, actually. Let me erase this. It's too big. Okay. So what do we mean by the longest prefix wins? Let's say I'm a router over here. Got a router over here and a router over here. This is R1. This is R2. And this is R3. And I got a user here. And that user is 172.16.00/24. So my source IP is 172.16.0.5. And R3 here, let's say, actually no, I don't want to do 172. R3 here has the 10.0/0/0/24 network, and R2 here has the 10.0.0.0/26 network. Now, just looking at this, which one is the longest prefix? Well, /26 is longer. Really what we mean by that is what is the bigger number in our subnet mask here? Because remember, R1 is going to learn about these remote subnets. We're building the best paths in our routing table. So R1 is going to have its routing table here, okay? 1 second, guys. Okay. So let's say our computer here, so we're going to learn about these routes. So let's say this is OSPF, and this is OSPF. So we're learning about these via OSPF. So 10.0.0.0/26, 10.0.0.0/24, and let's say this is gig 00, this is gig 01. So we're learning about this one via gig 0/1, we're learning about this one via gig 0/0. We built our network. Okay. So when this PC wants to talk to 10.0.0.0.6, which way is it going to go? Well, when R1 receives that destination IP, because remember, this is our layer 3 header, that's the destination IP, it's going to reference its routing table. And it's going to say, this is its routing table. It's going to say, okay, I have 2 paths here. This is a 0, okay? One is 10.0.0/26 and one is 10.0.0/24. So I have 2 ways that my user can reach 10.0.0.6. But out of these 2, I am picking the /26 because it is the longer prefix. It's the longer prefix of the 2, So I'm going to choose to send that traffic out over to R2. That's the rule of longer prefix, okay? Now let's say we have this scenario though, where our user is trying to get to 10.0.0.90. Well, now we're going to receive that destination IP. We're going to reference the routing table. Now which way is it going to choose? /26 is still the longer prefix, right? Yes, it is. But 10.0.0/26, that IP range is .0 to .63. .90 is outside of that range. So actually this route doesn't match this. This IP address is out of the range for this route. So now our only option is that /24, okay? That's how the longest prefix works. Now you may be asking me, well, what if we have a scenario like this, where it's a /24 from both sides, but one is EIGRP and one is OSPF. Well, in this scenario, the prefix lists are the exact same, but now we're learning about it from two different routing protocols. So now how do we choose which path we're going to use? So we come back over here, let's determine that. So if the prefixes are the same, so we don't have to worry about the longest prefix matches, right? If the prefix lists are the same, the lowest administrative distance is going to be used. Say, what? That's a new word. What's the administrative distance? The administrative distance is the trustworthiness of a routing protocol according to that router. So remember in our scenario, we're learning about the 10.0.0./24 network from EIGRP and OSPF. So the prefix lists are the same. It's a /24. But every routing protocol has a set administrative distance, and the lower is better, and this indicates the trustworthiness of a route. So between EIGRP and OSPF, which one is going to be preferred? EIGRP, because it has a lower administrative distance. So this administrative distances are in the slides that we can reference in your Google Drive, okay? Because it will be something you need to memorize, these administrative distances. So lower is better. So that's easy. So in that scenario, this is easy. We're going to choose the EIGRP here because it has the lower administrative distance. So this is administrative distance. Okay, piece of cake, right? Piece of cake. Now, let's add in another variable. Let's say we're learning about both of these via EIGRP. Actually, let's say we're learning about both of them via OSPF. Okay, so this is OSPF. This is OSPF. So we're learning about both of them via OSPF. So you have that little O code. That's an O, right? Not a 0. But let's say this is fast Ethernet 00. It's fast Ethernet 00. So let's go through our rules again. So the prefix list is the same. So there is no longer prefix that we would be preferring. The administrative distance is the same. It's both OSPF. So the administrative distance is both 110. So now, when the prefix is the same, the administrative distance is the same, we go with what's called the best cost or the best metric, okay? So OSPF's metric, and this is specific to OSPF, but the logic is the same. Like if EIGRP you have a lower metric, then it's better. OSPF, the lower the cost, the better. So what is that though? What is the cost? What is the metric in OSPF? So in OSPF, specific to OSPF, that's bandwidth. But this is also the same for RIP and EIGRP. The lower the metric, whatever their metric is better. So in OSPF, their metric is a reference bandwidth divided by actual bandwidth. Okay? And actually, just for simplicity reasons, we're going to say this is Ethernet. So that's like 10 megs, okay? So that reference bandwidth is 100 megabits, divided by the actual bandwidth. So if we're getting the metric between R1 and R2 and R1 and R3, here's the algorithm. So for R1 to R2, it's going to be 100 megabits divided by 1,000 megabits. That's going to equal 1. Now, I know some of you are saying you're crazy. That's 0.01, but there's no decimals, okay? And then from the path of R1 to R3, Ethernet is 100 megabits divided by 10 megabits. That equals 10. Okay, that equals, right? Yeah, that's 10. So out of this scenario, which one would be preferred? Obviously, gig 01. Now, we can look at this and say, no shit, right? It gigabits faster. But how does OSPF know it? It's this, reference bandwidth divided by actual bandwidth. So R1 to R2, that path is going to be better. That's a bandwidth of 1, or excuse me, the cost is 1. The cost is 1. And from R1 to R3, according to our algorithm here, reference bandwidth divided by actual bandwidth, the cost is 10, which of course is higher. Lower is better. So that's how we determine the best routes, the best path to place in our routing table. It's the longest prefix is the first rule. Longest prefix inclusive of the destination IP is always preferred. 2, if the prefixes are the same, that's also subnet mask, whatever, right? Then it's going to go into lower administrative distance. So which routing protocol is the lowest administrative distance? If that's the same, we're learning about all of our neighbors via OSPF, then it's going to go into the best cost, the lowest metric, the lowest cost, okay? So now let's take a look at this again. I'm going to erase this just so it doesn't look clean. So we have our old little design here as well, which pretty much is the same thing, right? Showing us between R2 and R4 and R3, the same networks are being advertised here, but what are we going to prefer, okay? So now let's look at a routing table. Let's try to read this routing table. So this, whoa, what just happened? 1 sec. Oh, I have my eraser still on. Okay, so we do show IP route on like a Cisco routing table. What's going to be over here is going to be what's called our code, so how we learned about it. Then it's going to be the actual subnet. And then this bracket right here, guys, this first number is the administrative distance. This next number is the metric. This via is the next hop. And then we have our interface, which is the next hop. So we look at it over here in a little bit more clear view, what a selection in the routing table looks like. We have our routing source. So R equals RIP, O equals OSPF, D equals ERGRP, S equals static, B equals BGP. You can see here, but like I'll show you actually. When you look at the routing table on a live device, it tells you what these codes mean. The next IP address is the destination network. That's a network, so it's a /28. In these brackets, the first number is the administrative distance. Next is the metric. After this via, this IP address here is the next hop. The route timestamp, so how long we've known about it, okay? And then the outgoing interface. That's how we read entries in our routing table. Alrighty, I think that's it for routing. So just to cap it all together, go over our slides, right? Route selection prefix length is going to be preferred. So in this little scenario, if I'm trying to reach 192.168.0.20, based off this little routing table, which one am I choosing? This RIP route, because the /27 is the longest prefix inclusive of this IP. Now, if we made this .50, which one are we going to prefer now? We're actually going to prefer this ISIS route, because even though /27 is longer, that range is only .0 to .31. So this IP address is not inclusive of this subnet. So that's no longer an option. So now the next longest prefix list, inclusive of the destination IP, is /26. Okay, and then if the prefix lists are the same, we go over administrative distance. Use the administrative distances I want you to learn. So if we're directly connected, that just means like the LAN off your router, your AD value is 0. A static route is 1. eBGP is 20. Internal EIGRP is 90. OSPF is 110. ISIS is 115. And then RIP is 120. Okay, and then if the administrative distance is the same, we go based off the metric. So here's the different metrics. The only thing you really have to know, guys, is that for OSPF, its cost is bandwidth. Its metric is bandwidth, okay? That's what you'll see on the exam. Okay, that was a lot. So I started teaching again at 6:05. Can we go through this quickly? Okay, let's go ahead and take another, because that was like the bulk of like this day 3 training, just getting through routing. Switching and Wi-Fi will be a little easier. That'll just kind of be more like, let's just look at the slides and memorize this stuff. Yeah, let's take a 10-minute break, give my voice a rest. We'll come back at 6:43 and we'll finish up routing, and then we'll jump into switching as well, and that'll be quicker. All right, guys, let's go ahead and jump back into it. Let's finish up this section here. So now we're going to go over network address translation. So this is another technique that, well, this is a technology that does typically live on the router. This transforms private IPs to public IPs. Remember we talked about this, I think the very first day we went over IP addressing. RFC 1918 addresses, those are private IPv4 addresses that are used because of the exhaustion of public IPv4, because we were running out of IPv4 addresses. So the technique we came up with was network address translation. We set aside 3 subnets of private IP addresses to be used for anybody. So with NAT, what we do is we have our private IP address range, and we translate those private IPs into our single public IP. So NAT hides the internal IP addressing, adds a layer of privacy, but also just enables us to talk on the internet with our private IPs. So that's the very fundamentals of NAT. Now we have 3 different types of NAT. We have static NAT, dynamic NAT, and then port address translation. What you're using right now to be able to connect to this Zoom call, to be able to listen to me talk, is port address translation. This allows you to have a single public IP address that can be used to translate hundreds or thousands of private IP addresses. The way it does this is it tracks your socket, your entire socket. Your socket is going to be your layer 3 and your layer 4 header, specifically the port numbers in your layer 4 header. So what port address translation does is it takes your transmission from your private IP address, so it'll have your source IP, your source port, it'll have your destination IP, your destination port, it'll translate your source IP into its public IP on the outside interface. I'll draw this up in just a second. And then it's going to maintain a table that says, hey, on the transmission back, when the server replies to us, connecting to us on port, whatever your original source port was, make sure we send that to our private IP address. So here's how it looks with port address translation. I'm going to bring up another whiteboard to demonstrate this. So let's say we have our router. So this is our PAT-enabled router, connected to some ISP, and we have our server here that we want to reach. This is going to be a public server, whatever it is. So we have our outside interface here. This is our outside interface. Outside IP, outside interface. So let's say this is a public IP, 2110/31. So right here we have .1. And then our inside network is going to be a private IP, 10.0.0.0/24. So let's say this is our computer here, our PC. This is .10.0.0.5. Okay, and this PC wants to reach this web server. So here's how it's going to start. So we're going to have to build our entire packet. So let me pick a different color here. Okay, so this is, let's say, PC1. So PC1, it's going to build its layer 3 header. So this is our layer 3 header. And this is our source IP and our destination IP. So our source IP is 10.0.0.5. Our destination is 17.1.1.3. And then we're trying to reach this web server via, let's say, HTTPS. Then we're going to have our layer 4 header. Actually, let me make that a little cleaner. This is going to be our layer 4 header. And in that layer 4 header, we're going to have a source port and a destination port. So that source port is just going to be something like ephemeral. Let's just say it's like, I don't know, 10001. And then the destination port is 443. So we're doing HTTPS. So in this packet, this entire packet, we call it a socket, right? When we add that layer 4 header. When it hits our PAT-enabled router, here's what's going to happen. Is we're going to translate that source IP. We're going to translate that source IP into our public IP here. We're going to keep the destination IP the same. And then our layer 4 header is also going to be the same. But what we're going to do is we're going to build what's called a NAT table. And I'm going to draw this over here. We're going to maintain what's called a NAT table. And in that table, we're going to track this translation. So we're going to say, hey, 10.0.0.5 :1001 was translated into 2.1.1.1 :1001. So we know that translation, okay? So once this packet finally reaches the destination, the server gets that and say, okay, you're trying to do an HTTP session to me, so now let me talk back to you. So what's it going to put on the packet back? So here's how that packet back is going to look. Now this is from the server, right? Let's say this is our client. This is from the server. So it's still going to have its source IP, which is 17.1.1.3. Destination IP is going to be what? 2.1.1.1. And then what do we have for our layer 4 header? For our layer 4 header, our source port is going to be 443. And what's our destination port going to be? It's going to be 10001. That's how we receive, this is like, we're pretty much just rebuilding it, just in opposite order. Okay. Now when this packet reaches our PAT-enabled router, it's going to say, okay, someone is trying to talk to me on port 10001. Well, now I can reference my NAT table here and say, oh, 1001, that belongs to my private IP off 10.0.0.5. That's PC1 here. So then it's going to translate it back. So now it's going to say, cool. So actually, you're trying to get your destination IP is actually going to 10.0.0.5. Remember, this is from the server on the way back now. And I know that because I maintained that table that was mapping you to this port. So once I saw that they were destined for this port number, I knew it belonged to 10.0.0.5. And that is how you're communicating as we speak on this Zoom call. That's what's happening on the wire, on your PAT-enabled router, okay? All right, moving on. Next, last routing technology we're going to talk about, then we'll move on to switching, is FHRP, the first hop redundancy protocol. This allows us to have pretty much fault tolerance for our routing devices, okay? This allows us to have fault tolerance for our routing devices. So we have a couple of different first hop redundancy protocols we're going to talk about. HSRP, which is Cisco proprietary. Then we have VRRP, which is multi-vendor. And then we have GLBP, which is also proprietary, that also allows load balancing. It's called the Gateway Load Balancing Protocol. HSRP stands for the Hot Standby Routing Protocol, and then VRRP stands for the Virtual Router Redundancy Protocol. HSRP and GLBP are Cisco proprietary, and VRRP is multi-vendor. I guess you could call it, it's not, yeah, open source, whatever. So when we don't have FHRP, we don't have this redundancy in our default gateways. This allows us to have redundancy. It allows us to have two devices, both with internet connections out, that can service our users here. One will be the primary. That'll be the primary default gateway that our users talk to. And if that primary default gateway ever goes down, it'll transition over to the secondary that can also be used. It's supposed to be kind of like a simultaneous switchover. So the first one we're going to talk about is HSRP, the Hot Standby Router Protocol. as I said, redundancy, it's router protocol. This is a Cisco proprietary protocol designed to provide gateway redundancy. Pretty much how it works is when we configure HSRP, is R1 and R2 are going to do an election of who will be the primary, which means active. They're going to share a virtual IP address. They're going to share a virtual MAC address. This virtual MAC and this virtual IP is what your PCs, your users, your end devices are going to use to talk out. So their default gateway will be this virtual IP that is being shared between R1 and R2. And the active one will actually be taking the connections. And then if the active one fails, the standby will take over. VRRP does the exact same thing, guys, except they call it master and backup, but it does the same thing. They're going to share a virtual IP and a virtual MAC address that our end users will use to communicate to the default gateway. The master will take all those connections, and if it fails, the backup will take over. Remember, this is multi-vendor. Okay, now let's move on to our switches. If you want to do the quiz, that's domain 2.1.1. I just don't want to do it, not waste time, but I just want to get through all of domain 2 today. Okay, so domain 2.2.1. I know it feels like, dang, we spent a lot of time on routing, but I hope you can kind of see why. You know, I feel like routing is kind of like it's heavy, right? I think that's probably the heaviest section besides our IP address section. Everything else is just going to kind of go quick now. We just got to memorize some things on our PowerPoints for our exam. Okay, domain 2.2.1. Given a scenario, configure switching technologies and features. Spanning tree protocol, that is also pretty heavy too. I'm just going to keep it simple here because they don't go deep into spanning tree protocol. Okay. All right, so first thing we're going to talk about, guys, in our switching technologies is going to be VLANs. That's virtual local area networks. So VLANs are how we logically segment our layer 2 infrastructure, pretty much our campus networks. What it does is it's going to take, it's going to allow us to have multiple subnets to be used in our LAN. And what it does is it's going to insert a VLAN header into the Ethernet frame. That header is going to tag that traffic. We call that tagged traffic. It's going to have a VLAN tag on it. And it's going to designate the data in this frame as part of that VLAN ID, which is literally a number 1 through 4094. Okay? The standard we use for VLANs is called 802.1q. The IEEE 802.1q. That is the standard, the encapsulation standard we use for VLANs, okay? So you can see here literally what this does is we have this switch here that has 4 different VLANs. You can see each VLAN has its own subnet. So each VLAN is tied to its own broadcast domain. So if my systems in VLAN 8 want to talk to VLAN 11, these live on entirely different subnets. So the switch will not be able to switch traffic between them. They will not have reachability here if we just have VLAN 8 and VLAN 11 here. What we need to do is make sure that we have a layer 3 device that can route between these different subnets. So VLANs designate different broadcast domains, different subnets in our LAN. They do this by, again, inserting that VLAN tag into the frame. So how this would be configured, just from the switching perspective, let's get rid of that layer 3 there. Let's say we didn't have that. Just from the switching perspective, is let's say this would be gig 0/1. This is gig 0/2. The configuration would be switch port, access, VLAN 8. So now any device that gets attached to gig 01, anytime we send a frame inbound to our switch, or we're just sending traffic, right? We're sending traffic to that switch, it's going to tag it with VLAN 8. It's going to insert that VLAN 8 tag into the frame. Same over here. Gig 02 would be switch port, access, VLAN 11. And now any device that gets plugged into gig 02 is going to get tagged with VLAN 11. And literally, if I could like show you inside of this little tag, it's just going to be like VLAN ID colon 8, VLAN ID colon 11. But those are also tied to their own subnets, okay? Yep, that's pretty much good for VLANs, okay? So let me mention one more thing here on this slide. VLANs can span across switches. And what I mean by that is in our campus network, we may have 10, 20, 50 switches that all share the same VLANs. So VLAN 8 here can be on both these switches. VLAN 10, VLAN 20 are on both of these switches. So this interface here that's connecting the switches, you may ask, what VLAN is that part of? It's not part of any VLAN, it's part of what's called a trunk. A trunk allows inter-VLAN traffic between switches. It allows all tagged traffic on that interface, okay? It allows all tagged traffic on an interface, trunk. So trunk ports are configured from switch to switch and switch to router, okay? Switch virtual interfaces. So now, how do we make, I keep talking about like multi-layer switches, layer 3 switches. How is that done? That's what's called a switched virtual interface. So a switch virtual interface is going to allow you to put IP addressing on that switch. So if we look at our configuration here, it's pretty simple in the way it does this. So when we create our VLANs, like this command here, VLAN 10, and we name it sales, that's a layer 2 function. That's pretty much saying, hey, switch, I'm going to configure some access ports here, and those access ports are going to be part of VLAN 10, so make sure you insert that VLAN 10 tag on traffic inbound on that interface, right? But then if I want to put IP addressing for that VLAN, because remember, VLANs represent its own broadcast domain, we do that with what's called a switch virtual interface. And on a Cisco device, the configuration is pretty simple. It's just interface VLAN 10. So now we're saying, hey, this is my layer 3 interface for this VLAN tag here. And then we just give it an IP address. And now this will become our default gateway. So now a user here is on VLAN 10. So that means gig 02. We said switch port access VLAN 10. So now we're tagging traffic inbound here on gig 02 with VLAN 10. We're inserting that VLAN header. And then we're saying, if you want to be able to be routed, your default gateway lives on SVI 10, interface VLAN 10 here, at this distro layer switch, okay? So that's how we configure SVIs. And that's what makes our switches multi-layer switches. Now let's go into other specific types of VLANs. So we have VLAN types here. So we have the native VLAN. So the native VLAN is that default VLAN. So if I take a switch out of the box and I open it up, every switch is going to be on VLAN 1. That's the default VLAN, or what we call the native VLAN, okay? That native VLAN is considered untagged because it doesn't have a VLAN header on that Ethernet frame that says VLAN ID 1. It doesn't have this. So even though we call it the native VLAN, you're not really tagging it, but I know it's a little confused, but that's what it is. It's untagged traffic coming across a trunk link. That's what we call the native quote-unquote VLAN, okay? Then we have the voice VLAN. And again, obviously you may realize, like, is he holding back a little bit of information? Kind of, but for the Net Plus exam, untagged traffic is considered the native VLAN, okay? Okay, the voice VLAN. The voice VLAN is a Cisco proprietary thing that is configured the same way. Like you see the configuration here, switch port voice VLAN 10. So essentially what that does, it's a special VLAN that says, hey, if you're putting voice VLAN 10 on this interface, you need to plug a Cisco phone in, and I'm going to assign it quality of service tags at the actual layer 2 interface, okay? It's specific for VoIP traffic. Down here too, you can see the native VLAN by default is VLAN 1, right? And that's considered untagged traffic. If you want to change that for security purposes, which you should, because if I know that the native VLAN's always VLAN 1, so does an attacker, you can change that by using this command here, switchport trunk native VLAN 20. And you do that on the trunk ports, okay? So if you change the native VLAN on the trunk port here at switch 1, you have to do it over here on switch 2. It has to be the same all throughout our environment. The 802.1q tagging, which I already talked about, 802.1q, that's the IEEE standard for VLAN tagging, okay? All right, the next layer 2 technology we're going to talk about is something called link aggregation. So link aggregation goes by many names: port channeling, ether channeling, port bundling, lag, which is like link aggregation, right? NIC teaming, if you're from the server side, on the sysadmin side. Whatever you call it, link aggregation is a technique that takes physical interfaces and bundles them into one logical interface to increase your bandwidth, okay? So here is an example. It's port bundling. We took 4 1 gigabit per second speeds and bundled them to a single logical interface. So even on the actual wire, you know, this may be, like all these interfaces may be gig 00 through 3. When we create an ether channel or a port bundle or a port channel or link aggregation, all synonymous, we're creating a single logical interface like port channel 10. That's port channel 10, right? And now that's the single interface that traffic is going to come across. So now each switch recognizes that as port channel 10. Now there's a bunch of different ways you can configure this. On a Cisco switch, if we're configuring link aggregation, what they call ether channel, and you create that port channel, there's 2 different negotiation protocols that the switches will exchange to create that ether channel, that port channel. PAG-P is a Cisco proprietary negotiation protocol for your ether channels, and LACP is the multi-vendor protocol, meaning any vendor can use LACP. That's as far as I'm going to go with this, okay? That's what you need to know. That link aggregation allows you to take your physical interfaces and bundle them into a single logical interface for increased bandwidth. And that PAG-P is the Cisco proprietary protocol, negotiation protocol for Ether channel. Pretty much when I say negotiation, when you configure it, you can see here mode desirable, which means PAG-P. It just means we're going to start sending messages to the other side saying, let's form an Ether channel, okay? LACP is the other negotiation protocol, and that's multi-vendor. Okay, speed and duplex. So we can change the speed and duplex setting on our interfaces on a switch. So if I have a gig 00 interface, that's gigabit Ethernet, that means I have speeds of 1,000 megabits per second, right? I can actually hard set that. I could, for some reason, make it less, and I can also change the duplex. So duplex is we have 2 different types of duplex, full and half. With full duplex, we can send and receive traffic on a single interface. We can send and receive, meaning whatever is connected to this switch, computer on gig 00, if it's full duplex, I can send and I can receive at the exact same time. With half duplex, it's send or receive. So if half duplex, if I'm sending, I can't be receiving at the same time. So we can also hard set that. Usually these things are auto though, but the Net Plus wants you to know what these are and that you can hard set them. Okay, spanning tree protocol. Man, this is such a deep topic, and when I teach this in CCNA, we spend like an hour and a half on this. For the Network Plus exam though, you know, it doesn't dive deep. You don't need to know the different spanning tree protocols, how it does its election. Really, you just need to know what it prevents, right? What spanning tree protocol prevents. So, in switching, kind of to explain spanning tree, we got to explain how switches forward frames, how they forward traffic, okay? So, switches have what's called a CAM table or MAC address table. It has a MAC address table. MAC address table. That MAC address table is going to be populated by all the devices plugged into that switch. So pretty much if I have a computer here and its MAC address is Bravo Bravo, which we know that's not it. MAC addresses are 12 hexadecimal digits. So hexadecimal is 0 through 9 and A through F, right? But just for an example, let's say it's BB. When I create my layer 2 frame and I send traffic here and I'm hanging off gig 01 here, I'm going to populate a MAC address table. And that MAC address table is going to say, hey, gig01 has MAC address BB. And then when I connect another device here, and this MAC address is Charlie Charlie, and this is hanging off gig 0/6, it's going to say gig 0/6, MAC address Charlie Charlie lives there. And then when these two want to talk to each other, I'm going to make a layer 2 header with the source and destination MAC address. The switch is going to look at my destination MAC address, and it's going to say, oh, you're trying to talk to Charlie Charlie. That lives off my gig 06 interface. I'm going to send you out that way, okay? That's basic switching. So now you may ask, well, what if I have this computer over here whose MAC address is 69, and I don't know where to send that? What's going to happen? So I got this computer BB that wants to send traffic over here to this MAC address 69. So build that frame. The switch looks at it, references the MAC address table, and says, I have no idea where to send that. What the switch does is then it does something called frame flooding. It's going to take that frame from that user, and it's going to flood it out all of its interfaces. It's going to flood it out all of its interfaces. Well, when the switch does that, let's say this is switch 2, switch 1, this is switch 3. You see how all these switches are interconnected, right? We have redundancy here. That's good. So it's going to flood the frame when it doesn't know where to send, right? It doesn't have like an entry in the MAC address table. Well, switch 1 receives that, switch 3 receives that, and guess what it's going to do? It's going to take that broadcast MAC address and also flood it. One thing it doesn't do, though, it doesn't send it back out the interface it received it on. So it'll just send it out here, and switch 3 will send it out this way. Well, then when switch 1 receives that broadcast frame from switch 3, it's going to send it out all of its interfaces besides the one it came in on. Switch 3 is going to do the same thing. I hope you see where I'm going with this. Switch 2 is going to receive that broadcast frame from switch 3. It's going to send it out the active interface besides the one it came in on. It's going to do the same thing from the broadcast frame it got from switch 1. And it's going to keep doing that. And it's going to keep doing that and keep doing that till all of its CPU utilization is throttled. And then we get something called a broadcast storm. Or a switching loop. Okay? That's no good. What spanning tree protocol does, guys, is it prevents that. It prevents that by electing what's called a root bridge. Once it elects the root bridge, that's the king of the castle. There's the king. It elects the root bridge by something called the lowest bridge ID. The rest of the non-root bridges are going to determine the shortest path. Once it determines the shortest path, spanning tree protocol is doing all this. It's going to block a redundant port. So now when we do those broadcast frames, broadcast messages can't go out this port, and that's going to stop that broadcast storm. Okay? Now you may say, that's awesome, spanning tree does that, but what happened to redundancy? Well, if the primary ports go down, that one that we're blocking, it'll go to a forwarding state, okay? Spanning tree protocol knows that. It knows that we made this one blocking because we're preventing broadcast storms. So if our primary one goes down, it's going to turn this into a forwarding port, okay? When I made this slide, like I had the idea is to go deep dive into spanning tree, but for these live virtual training sessions, I'm just trying to get you guys like boot camp style ready for the exam. So all you need to know for spanning tree protocol is that it prevents broadcast storms. And the 2 steps it does that by is it elects a root bridge, and then it determines the shortest path to the root bridge from the non-root switches. And then once it does that, it just blocks the redundant ports, okay? But it doesn't dive any deeper into that on the exam, okay? If you want to deep dive on this, if you check out my YouTube channel, we do a deep dive on spanning tree on there, on the CCNA section. Okay, and then we have the different types. We have rapid spanning tree and multiple spanning tree. Again, I just put that on there. They don't really ask that on the exam, but rapid spanning tree is the quickest, okay? It converges the fastest. It does this process, this electing, terminating short path, blocking redundant ports in 2 to 4 seconds. Okay, last thing we're going to talk about is MTU, so maximum transmission unit. So the maximum transmissions unit is the size of an individual packet. So by default, in an Ethernet network, the maximum transmission unit is 1500 bytes. That's a normal size. So 1500 bytes to include all the headers, the layer 2, 3, 4, 5 headers you need, and your actual data that you're sending across, okay? Now, we have something called jumbo frames, where we can actually say, hey, each frame, each packet, we're gonna make the MTU a 9,000 bytes in size, okay? So that's the MTU, the maximum transmissions unit is 1500 bytes by default. And then we can configure something called jumbo frames, which can go up to 9,000 bytes in size, but that's something we have to actually set on a per interface basis. Okay, awesome. So that is domain 2.2. Let's go ahead and take another 10-minute break, and we'll go over Wi-Fi next. All right, guys, let's go ahead and finish up domain 2. Let's head on to domain 2.3. So this is all about wireless devices and technologies. So we're not gonna I'm not gonna dive into like a wireless LAN controller or an access point and do any configuration like that, like you saw me do with the routing. But what we will do is go over the fundamentals of wireless. We're gonna go the different frequency options, which pretty much means like all the different 802.11 standards and the network types, and also define what an SSID is. Okay, so wireless channels. So wireless networks operate using what we call channels. These are frequencies, radio frequencies, or frequency bands that are emitted from your access point to Wi-Fi enabled devices to make that connection. And once we make that connection between Wi-Fi enabled device, that's your laptop, your phones, to access point, that access point then pushes your data to the wired backbone. So that's your campus network, your switches. So we have 3 major ranges of wireless networks or channels. So we have 2.4 gigahertz range, we have the 5 gigahertz range, and then we also have the 6 gigahertz range. Now, in each range, we're gonna have channels. So in the 2.4 gigahertz range, those are gonna be 20 megahertz channels. So that's the narrowest option. So without getting into what these cycles, these megahertz actually means, essentially what you need to know for the exam is the smaller the channel, the less bandwidth and throughput you have. So in the 2.4 gigahertz band, we have 20 megahertz channels. Those are the narrowest. They're going to have lower data rates. Then we have the 40 megahertz channels, which we see right here. They get a little bigger, right? Their bandwidth gets a little bit more. We can achieve that in the 2.4 gigahertz range if we want to do something called channel bonding, but it's not typical. And then we have the 80 and 160 megahertz range. And as you can see right here in this chart, this is the 5 gigahertz range. So you see the 5.1070 megahertz to 5,835 megahertz. You can see the bigger the channels, the more it takes up in that range, okay? So it's just it's a simple equation. The bigger the channel, the more bandwidth. Now to dive in more of these wireless channels, one thing we have to worry about in our 2.4 gigahertz range is something called non-overlapping channels. So here in our chart, we have the 2.4 gigahertz range. You can see it's from 2.4 to 2.5 gigahertz. And we have 14 channels in there. 14 20 megahertz channels. Now the channels are labeled 1 through 14, and the only ones that are not overlapping are 1, 6, and 11. You need to know that. So the only non-overlapping channels in the 2.4 gigahertz range is 1, 6, and 11. Now in the 5 gigahertz band range, there are more non-overlapping channels due to a wider range of available frequencies. So you don't really have to worry about it as much because we have such a big range in the 5 gigahertz. We also have to worry about regulatory impacts. So what we mean by that is pretty much these frequencies are designated by the FCC in America. So they say, hey, for Wi-Fi, you're going to have these frequency ranges, and that's what you have to use. So then we have regulatory impact. So sometimes radar systems are going to operate on the same bands as Wi-Fi, and so that's why we have these certain channels here. So 802.11h. So regulatory impacts refer to the rules and regulations that wireless devices must follow depending on the country or region. To comply with these regulations, certain features were added to Wi-Fi standards. One of the key regulatory standards is the 802.11h standard, which is an amendment to the original 802.11 standard. 802.11, guys, that's the wireless frame standard. So you know in Ethernet, you have your copper, you have your Cat5, that's 802.3 Ethernet. 802.11 is the wireless frame standard. So it addresses 2 things. DFS, dynamic frequency selection. This prevents interference with radar systems by automatically shifting the Wi-Fi signal to a different channel if radar activity is detected. And then also TPC, transmit power control. Adjust the transmit power of wireless device to minimize interference and reduce signal range when necessary. What we're saying there is like, hey, you can't, as a manufacturer, you can't build an antenna that's so powerful that it shoots that Wi-Fi signal all throughout the neighborhood and blocks everybody else, right? So that's pretty much what we mean by transmit power control. Okay, then here's our frequency options, just actually labeled like here for you with the 2.4, the 5, and the 6. So just some key things about this. The 2.4 gigahertz range It's technically less bandwidth and throughput, but it goes farther. So what I mean by that essentially is like if I put an access point in the middle of a football field and I turn on the 2.4 gigahertz range on that access point, it's going to reach the entire football field. You'll have a pretty strong signal from, if I place the access point at the 100-yard line and you go to the other end, you'll have a strong signal still from like a phone to a weak access point because it's easy to spread, okay? Now without getting into like actual RF theory, because we don't really need to in the Net Plus, the 2.4 gigahertz range can go a lot farther and it goes through objects a lot easier. So if you're in your house and your access point's in your living room, you're in a big house, you have a single access point, you go to your room and you try to connect to the 5 gigahertz range, you're gonna have a weak signal. Yes, it's more bandwidth, but it's a weak signal because it has to go through all those walls. Where the 2.4 gigahertz range goes through objects a lot easier. Now 5 gigahertz bandwidth, it offers faster speeds and less channel interference, but the signal range is shorter. So you see it written here. It doesn't penetrate walls as well. It's for short range connection. So if you're in the same room, like it's a 5 gigahertz range access point, then that's what you should go with, right? And then 6 gigahertz range is pretty much the same logic, right? More bandwidth, less channel interference, significantly more non-overlapping channels, but the range is limited. And it requires more power, right? The stronger the signal, the more power it requires. So you need these beefier access points, better antennas, things like that. One thing we're going to talk about here is band steering as well. So band steering is a feature used by modern wireless routers and access points to automatically direct dual band devices to connect to 5 or 6 gigahertz instead of the congested 2.4 gigahertz band, and vice versa. Pretty much just allows that device to, like it's like a smart feature. Like, oh, hey, I noticed there's a lot of congestion on this range, so I'm going to connect to the SSID emitting on the 5 gigahertz range. Okay, an SSID. An SSID stands for Service Set Identifier. It's the name of a wireless network that is being broadcasted by the access point. I think I talked about this on day one. Remember, an SSID is a name that's being broadcasted that represents a wireless network. So imagine we have 3 different VLANs, the sales, accounting, and marketing VLANs. And we have a Wi-Fi network in our enterprise. So an access point can emit 3 different wireless networks using 3 different SSIDs that correlate to those 3 different VLANs, which are 3 different broadcasting domains and 3 different subnets. That's what an SSID recognizes, the wireless network. So a single access point can emit multiple SSIDs. The basic service set identifier is the MAC address of the specific access point that you're connected to within a wireless network. So within that wireless network, there's also a BSSID, which maps you to the actual hardware of that access point, okay? And then we have the extended service set identifier. So the ESSID is SSID of a network that consists of multiple access points. So imagine again we're in a big enterprise, we're in an airport, a bunch of huge office building with multiple stories, and we have to connect to the accounting VLAN, and we have a job where even though we're accountants, sometimes we have to go up and down for meetings, and we have to connect to our accounting network. Well, if we want seamless connectivity where we don't lose access, and we can connect to any access point we want while on the accounting wireless network, we have to configure ESSID. It allows us to roam, essentially. Gives us wireless roaming. Okay, mesh networks. So mesh networks consist of multiple access points that work together to provide coverage across, a wide area. So mesh networks are typically for like large homes. This is not something you scale out for an enterprise. Mesh networks are just a simple solution for larger areas that have like few users, right? They're usually, they are used with what's called autonomous access points, where an access point does your routing, your switching, your firewall, what you have at your house right now. On the contrary, in contrast to our enterprise, we have something called lightweight access points, where lightweight access points are controlled by a single wireless LAN controller, and we don't need to mesh them because all the routing and switching and firewall is done with that wireless LAN controller. And the only thing that an access point is doing is emitting a Wi-Fi signal. We'll learn about that in this section, 2.3.2. Okay, then an ad hoc network. This is a temporary network. Imagine this is like a Cat5 device between 2 computers, But instead of a physical cable, it's just two computers sending a signal to each other, a Wi-Fi signal from their wireless NICs. That's an ad hoc network. We have point-to-point. So you may be asking, well, what's the difference? Ad hoc is between two like compute nodes, where point-to-point on the other end of this, air fiber right here, this could be like a switch and a switch, right? So that's point-to-point. Essentially, imagine that's like a trunk port, okay? But instead, it's a long-distance air fiber connection that can go for a mile over, like, airports do this a lot on the runways. Okay, then infrastructure mode. Infrastructure mode is the most common network type for Wi-Fi networks. In this mode, wireless clients connect to an access point, which provides connectivity to the larger network. This mode is used in homes, offices, and public Wi-Fi networks. So essentially what we're saying here is like, hey, our access point, it's just getting you back to the backbone area. Instead of like this mesh, right, or this ad hoc, or this point-to-point, this is saying, hey, this is what a typical access point's doing, just connecting you to your routing domain and your switch domain. All right, moving on. We'll go over this section, and then we'll take another little break and finish up for the day going over domain 2.4.1. Okay, so continuing on with Wi-Fi, now we're going to go over the different Wi-Fi encryption, guest network authentication, just going over, hey, make sure you make a guest network, just some simple security. The different types of access points we have, we'll talk about autonomous and lightweight, and then the different types of antennas, like omnidirectional, unidirectional. Okay, so the encryption. So we do have encryption on our 802.11 frames, on our connections from Wi-Fi enabled device to our access point. So we have two different encryption standards. That's WPA2 and WPA3 that we're going to talk about. Yes, there was a WPA and there was a WEP before that are now vulnerable. So there was an original encryption called WEP, and then WPA came after, and those are deprecated. They're not secure. So now the two Wi-Fi standards we have that are secure are WPA2 and WPA3. So with Wi-Fi protected access 2 and 3, we use AES encryption. That's the symmetric encryption we use to encrypt the traffic from Wi-Fi enabled device to access point. And then we have two different modes. We have personal mode and enterprise mode. So for the authentication in all this, we have PSK, which is just a single password that you use to connect to that access point. It's what you use at your house. We call that WPA2 PSK or personal. Those are synonymous. WPA2-PSK or personal, that's the same thing. You just have a single shared key, a password, to connect to the Wi-Fi. Or we have WPA2 Enterprise, which is more robust. This is where we have an authentication server that sits outside it, it's not part of the access point, that's going to send your username and password over here. This will authenticate it and then authorize you to access that wireless network. So that's enterprise mode. That's where we have some sort of authentication server, some sort of identity provider. Then WPA3. WPA3 is it's upgraded, right? It's a new version. It uses AES, but it's going to have better bit key lengths. So WPA3 will use AES 128, 192, and 256. The longer the bit key length size, the better. It also gives us additional protections. It uses something called SAE for its pre-shared key, its personal connections. So simultaneous authentication at equals. This prevents brute force attacks, and that's for WPA3. So on your exam, if they ask what Wi-Fi protected access mode gives us protection against brute force attacks, it's WPA3 using SAE, okay? That also enables us to have what's called forward secrecy. So attackers cannot decrypt future sessions by stealing like our initialization vector is what it's called. You don't even know all that, just know that's what WPA3 provides. Okay, then guest networks. So when we set up a guest network, we have a couple different ways to do this. We can do this with captive portals. So this is where you connect to like the Starbucks-guest SSID. And instead of you using a pre-shared key, it brings you to a portal. And then in that portal, you have to put in a code or a password. But that's a way that we can track who's actually connecting to us, okay? And you may have to sign something or like agree to something on that captive portal that says you won't maliciously use this, right? So it allows us to authenticate users. display advertisements or messages. That's one way we want to set up our guest networks. Okay, just to kind of go into a little bit deeper, PSK versus enterprise. So with pre-shared keys, it's just a single password. With enterprise mode, that's using some sort of AAA server, typically with like Radius or 802.1x to authenticate and grant you network access. It's scalable. It lets you sync into your Active Directory, and this is what we use again for our like enterprises. Now antennas. So the actual antennas on our access point is going to determine our actual Wi-Fi range. So omnidirectional antennas are 360, right? They're meant to spread at 360, and they won't have as good as range because they're not, it's omnidirectional. It's not pointed. So the signal can be weaker at longer distances, but it has broader coverage. And then directional antennas, this is for like probably like, this is like purpose built, right? Like if you need a directional connection out to a single device, or you need that air fiber connection, that point-to-point connection, you have longer range, but not as broad. You can kind of see down here, unidirectional, it's going one way, while omnidirectional, it's going 360 coverage. Okay, then we have autonomous versus lightweight, and I kind of already talked about this, but with autonomous access points, this is what's at your house right now. This is an access point that's emitting that Wi-Fi signal. Users are connecting to it. And then that access point is doing the routing, the firewall connection, the switching, the DNS. It's doing everything for you. It's for small offices, it's for home offices, okay? Then we have lightweight access points. This is what you do in your enterprise. Lightweight access points are all controlled by a single server here called a wireless LAN controller. That wireless LAN controller pushes profiles down to these lightweight access points. It tells that lightweight access point what frequency range to be on. It tells that access point what SSIDs it's broadcasting. It tells it what encryption to use. It tells it everything to do. And that access point is just kind of dumb. It just has that connection back to the wireless LAN controller saying, tell me what to do. And the only thing that access point is doing now is just emitting a Wi-Fi signal for Wi-Fi enabled devices to connect to. That's it. Now, obviously, the advantage is this is for complex, scalable networks. But this is not good for small offices. If you just have a little spoke office, you probably don't need this. You only have like 5 users there. All right, cool. Let me make sure I didn't miss anything. I didn't go over the 802.11 ranges. Maybe that's in another section. Okay, that's fine. I think it's in a later section where we go over the ranges. So you see like 802.11, AC, AX, because that will be something you need to know for the exam. Actually, yeah, I think that's in domain 4, so that'll be like Thursday. Okay. I'm going to take another little 10-minute break. Let's come back at 7:57, and then I'll go over domain 2.4, and we'll finish up for the day, okay, guys? And then just to show you, while we have some time here, remember, you can access these slides on the Google Drive, so if you log into Academy. So domain 3 is pretty quick. As you can see, there's not too many slides. Thursday, we'll do domain 4, which again is even shorter. And we'll probably, on Thursday, we'll probably do some domain 5 just because how quick it is. And then we'll finish up Friday going over domain 5, okay? But all right, let's go ahead and take a 10-minute break. And we'll come up and we'll finish domain 2.4.